Hello everyone, let's try to implement full subtractor using Decoder IC 74LS138. We're going to implement it multisim, but first of all, let us see the truth table. So this is the truth table for sum, difference and borrow. Why did I say sum? I don't know. So this is the minute, subtract, and the borrow. So basically, we're doing a minus b and then minus this b in. So we'll first of all understand the truth table. So 0 minus 0 is 0 and 0 minus 0 is 0. So difference is 0, borrow is 0. So now 0 minus 0 is 0 again, and 0 minus 1 now see. For 0 minus 1 you'll have to take a borrow, so that's why borrow is 1, and 0 minus 1 is going to be 1, that's why difference is 1. And over here 0 minus 1 is again you'll have to take a borrow of 1, because 0 minus 1 you'll need a borrow, so we took a borrow of 1. 0 minus 1 is going to be 1 and 1 minus 0 is going to be 1, so this is 1. Then again 0 minus 1 is going to be, again you'll have to take a borrow, so you took a borrow, so 0 minus 1 is 1, and but 1 minus 1 is 0, so this is 1 0 now. So 1 minus 0 is going to be 1, borrow is going to be 0, no borrow, and again 1 minus 0 is going to be 1 and no borrow. So again the same thing, 1 minus 0 is 1, but 1 minus 1 is now 0, so it is 0 and borrow is nothing. 1 minus 1 is again 0 and 0 minus 0 is 0, so nothing, difference and borrow both are 0. 1 minus 1 is going to be 0, but now 0 minus 1 we need to borrow, so we took a borrow, but 0 minus 1 is 1, so difference is again 1. So this is the true table of full subtractor. So if you see the min terms, you see 1 for difference, that is for 1, 2, 4 and 7. So that's why we took here should be a summation sign, that is min terms, right? So that's why sum of product, so no, product of sum. So see, actually what is this thing? This is 1, 2, 4, 7, that is the min terms, and the same thing over here. So now let us try to implement in IC. So this is the IC. So let us connect simple things first. So this is the ground, we will connect it to ground. Enable is going to be connected to ground because they are active low, and active high will be connected to VCC. So this is the VCC, and this will be connected to G1, which is active high. And this is going to be A, B and C, but in reverse order because C is the MSB. But in a way it doesn't matter, but still A, B and C. A is the MSB and C is the MSB. Over here C is the MSB. Fine. So we connected MSB in such a way, for A, B and C, whatever. So now we just have to connect in for carry and, sorry, not carry, why am I saying carry always? Difference and borrow. So for difference 1, 2, 4, 7, right? So we'll do this thing, we'll connect 1, 2, we'll connect 4. Why am I taking only these wires? I'll tell you all. So see, what if you use a OR gate to connect them? Why am I using an OR gate? And you'll just use a probe or whatever, So see, if the sum is 0, that is see, for 0, 0, 0, if these all are 0, 0 and 0, then we want M0 to be selected, right? So this is actually M0. I will use a pen for that. So see, this is M0. My handwriting is really bad with the mouse. So M0, M1 and so on up to M7. So actually when the input is 0, M0 will get as 0. But when the input is 0, 0, 1, then M1 will be 1. So suppose the input is 0, 0 and 1. So M1 will be 1, that is Y1. M1 means Y1, remember, because we are connecting it in that way. So Y1 will be 1, but otherwise everyone else is going to be 0. So that's why all of these are going to be 0. So that is the advantage of using an OR gate. So for all gate, if any one of them is 1, then still the output is going to be 1. But see, now if you connect 0, 0 and 0, now what happens? Y0 is going to be 0, but otherwise everyone is going to be 0. Sorry, Y0 is going to be 1 actually. So Y0 is going to be 1, otherwise everyone else is going to be 0. So for everyone to be 0, the output is going to be 0 and our difference is going to be 0. So that's how it works. So this was for sum, and for borrow, that is we are going to connect 1, 2, 3, 7. So you can just assume me to connect 1, 2, 3, 7. So 1, 2, 3 and 7. So this looks really rubbish, but fine, whatever. I'm going to connect it to OR gate. But if you see, there is a bubble over here, which means that the output is going to be inverted. So actually what do they mean is, if the output is to be inverted by an OR gate, then A plus B is OR, that is A plus B complement is equals to A complement and B complement, right? So this is the De Morgan's law. So instead of connecting OR gate, we are simply going to use NAND gates. So over here in the previous thing, what we do, we'll just replace the OR gates by NAND gates. And why we are doing so is just because the input is going to be inverted. That's why we are just connecting it by using a NOR gate. Now let us implement in the multisim. That is going to be the next tutorial. So that's all from my side. Thank you.